All right. Good afternoon, everybody. Sorry about the delay in getting this recording out to you. I had a little bit of issue with my laptop this morning, so let me go ahead then and let me get started with this. Let me record the time here. Let me get this timer started. Um, hopefully you get a chance to watch this. Oh, sorry. Please make sure then that you have this. Obviously, been watching this, then you're already you're doing it. Yeah, we want to try to start. I want to start providing more lessons for you over the weekend, or try to use this time, at least post one for you, so that we can try to get through as much of the material as we can before the AP exam. Okay. All right, so let's go ahead. Let's get started. Let's quickly review where we left off with on Friday, yesterday, and that was we got started with the discussion of kinetics. And kinetics is the study of how fast a reaction or a process, any process, occurs. And so when we talk about and we want to be able to measure, we want to be able to determine in some way how fast a chemical process or a physical process occurs. A little bit more difficult with physical processes, but if we have a way to measure, okay, then we can go ahead and determine what we call a rate. Now, with that said, let me go ahead and try to use an analogy here that may help you. Okay, and so let me go ahead and let me open up my whiteboard here. Whoops, sorry, wrong one. Let me go ahead and open up my whiteboard here. And so we're talking about kinetics, and in the name itself, I think it becomes pretty apparent. We're talking about how fast something happens. Okay? So how fast something happens. Let me go ahead and I can share that with you. One of the more common ways that we measure how fast something happens is we often look at how fast an object, or say a car, travels over a given distance. Okay, so let's go ahead and let's examine what happens. Okay, so let's imagine then that this is the road right here, and we have a car on the road. There's our car. And for those of you who are taking physics or who will be taking physics, this is going to be pretty familiar, a familiar discussion to you, because this is something that you learn about in the first semester or first year of physics if you're taking AP physics, and the first semester of physics if you're taking regular physics. Okay? All right. So when we talk about rates, we typically are referring to a measure of some quantity, and I'll just call this X, some quantity over a period of time. Okay? So when we're measuring how fast something is moving, let's say how fast this car is moving, the rate that we are measuring, that rate then is going to measure how far something travels. So that means the distance that the car travels over a given time interval. So that we know then that a car that is moving faster will have a larger ratio here. The ratio between distance to time will be greater than a car that's traveling slower. So let's imagine then that this car here travels a distance. Let's say this car here travels a distance of let's say 10 meters. Okay, so we have a car traveling a distance of 10 meters. Okay. Now, and with that said, then that's the distance covered. But without a gauge, without an indication of time, it'd be very difficult for us to try to determine then how fast the car, how quickly the car is changing or covering this distance, how quickly this car is changing, covering this distance. And so we need an indication of time as well. So let's say then that this particular car covers this distance here. So we'll just car number one. Okay. It covers that distance in let's say then a 20-second time span. Okay. All right. So we were to calculate then for the rate, and that this rate then is what we refer to then as the speed. Okay. If all we're dealing with is the magnitude or velocity, if we are dealing with the magnitude and direction, but that's something you'll come across. Okay. So this rate then, which we call the speed, then is going to be defined then by the distance that the object covers, 10 meters, the car, over the time interval over which the object does that covers that time. So the rate here then is going to be about half a meter for every 1 second. Okay, so we reduce that, and that's the rate at which this car travels right here. Okay, now if we take a second car, and let's go ahead and do this here. We take a second car, and we allow that second car to cover the same distance. So let's go ahead and do this here. Okay, so there's car number 2. Okay, and that car is going to cover the same distance as car number 1. Okay, so there is the car. It's going to cover the same distance as car number 1. However, it covers it in a 40. So the time here, the time interval here, time for car number 2 is going to be, I'm sorry, let's say it covers in a 10-second time interval. The rate at which the car number 2 travels at is going to be then 10 meters for every, over a 10-second interval. Okay. So therefore, that rate then is going to be 1 meter per every 1 second. Okay. And so each one is, now with these two rates here, what we can do then is we can compare the two cars, and we can see then that car number 2 is going to be traveling at a much faster rate than car number 1. The car number 2 is traveling faster than car number 1. Okay. All right. So with that said, that's what rates allow us to do. Rates allow us then to compare what's the change that is occurring here. Okay, and so the change that's occurring here is the change in distance. We typically call that in physics displacement, okay, over time. And typically what we do then is to find this, not just the distance traveled, but the displacement here, we need to know then the position that each car starts out at initially. And here we'll call then that 0. And the position that the car ends up at the end of that time interval, and we'll call this 10 meters. So both cars undergo the same displacement. Okay, so if we define the rate that is distance over time, we've just calculated for the speed. Okay. If we define it then as displacement, this rate then as displacement over time, we have just calculated then for the velocity. Okay. And so that displacement then here takes into account this term displacement then. Now what we calculate for it, that it's going to be then the change in the position, okay, which means then it's going to be the final position minus the initial position. And in this case, then 10 minus 0, it's going to give us 10 meters in both cases. Okay. All right. So what we will, so that's what we do to find then the rate at which these cars travel. Okay. And so what we're going to be doing with when we talk about kinetics and chemical kinetics is we're going to do something very similar. But this time we're going to be analyzing different types of different reactions, and we're going to compare the different reactions in order to determine how fast or how slow the reactions occurring. And so instead of comparing displacement or distance traveled over time, we're going to be looking at the change. So instead of the change in position here, like we have them with the velocity, we'll be looking then at the change in concentration. Okay, and so that's what we can measure. We can measure the concentration. We can use a stopwatch to measure time, and if we get those two pieces of information, we can measure then what's called the rate of reaction. Okay, so let's go ahead then, and let me save this for you, and I will post it for you. Let's take a look at then an example of a chemical reaction that we can go ahead and do that with. Okay, so let's take a look. I left you. We left off with this this reaction here. Okay, so this is the reaction here that we wanted to examine the kinetics for. Okay, so we wanted, and if you notice here, what we're doing then is we will be looking at the concentrations of reactants and products as a function of time. That is, we are determining the rate. This is describing here the rate for the reaction and the rate of the consumption of NO2. So we're looking at the decomposition here of nitrogen dioxide. So we're going to compare then the rate at which nitrogen dioxide decomposes, and we're going to look at the rate at which nitrogen monoxide and oxygen forms. Okay, so the formation of each one of those. So let's go ahead then, and let's take a look at this and what we have here. Okay, all right. So we need then for the rate then, remember we have to define then a start and a finish. Okay, So let's go ahead then and let's look at the time interval here. Let's just examine the first time interval here, and let's just look at that set right there first. Okay, so let's look at that. And so if we take a look at this, then the initial concentration then, okay, and we have the final concentrations here. Okay, so we have the initial, that's going to be at time 0, okay, and then we're going to look at the concentration at time is equal to 50 seconds. Okay. All right, so let's go ahead. Let me pull up, let me open up my whiteboard again, and let's examine those values there. Okay, and let's take a look at what we have. Okay, okay, so let me go ahead and put this up here. All right, so we're looking at the time interval between 0 seconds. So the time interval between T initial, which is going to be at the very start at 0 seconds, and then the time interval at the end is going to be at 50 seconds. Okay. All right. So for let me go ahead and write this down here. The initial concentration, and just for those of you who don't have it, okay. So the concentration at time 0 for nitrogen dioxide is going to be then 0.0100 molar. Okay. At the 50 seconds end, we are at 0.0079. So that's going to be concentration final. This is concentration initial. Okay. All right. So let me go ahead and do the same for nitrogen monoxide and for oxygen. Okay. Hope so. We have then we don't start out with any here, and then at that's initial, and that's concentration initial, and then for the final, then we have then 0.0021 here, and then finally the concentration for oxygen. We don't start out with any initially, and we have then 0.0011. Okay, and these are all going to be molar. Now, first of all, I hope you can see then that we have a set of numbers that we can use. Okay, so what I'd like to do then is let's go ahead and let's calculate for first of all for the rate at which NO2 gets decomposed. Okay, so that's going to be then concentration of NO2. I'm sorry. So let me go ahead and do this. So we need the change in concentration. So sorry about this. Okay. So we need the change in the concentration of NO2 over the change in time. Okay, so remember with the analogy that I used with the velocity, it was the change in position over change in time. Here we have then that we're dealing with a chemical reaction. We're looking at the change in the concentration of nitrogen dioxide over time. Okay, so let's go ahead and plug that in. So it's going to be then the concentration of nitrogen dioxide final minus the concentration of nitrogen dioxide initial all over T final minus T initial. So let's go ahead and plug that in. Final concentration of nitrogen dioxide 0.0079. Okay, molar, okay, minus the initial concentration of 0.0100 molar all over the time interval of T final, which is 50 seconds, minus 0 seconds. And I get here a value that is negative 4.2 times 10 to the negative 5. And the units here are going to be molar per second. Okay. All right, so that's the rate at which, and this is the negative sign just indicates, and that's because you hopefully see here that that's negative. That indicates then that that's the rate at that's how quickly nitrogen dioxide gets consumed or it gets broken down, gets decomposed. Okay. All right, let's do the same thing then for the rate of nitrogen monoxide. Okay, that's going to be the change in the concentration of nitrogen monoxide over that same time interval, the change in time. That's going to be then nitrogen monoxide final minus the initial concentration of nitrogen monoxide, or T final minus T initial, come with the initial, right? And so therefore then we're going to have then 0.0021 minus 0 molar all over 50 seconds minus 0 seconds. And I get here a value of 4.2 times 10 to the minus 5 molar per second. Okay. All right. Finally, let's go ahead and I'm just going to quickly, well, I'm not going to try to narrate this too much. So I'm just going to write this down. The rate at which oxygen gets consumed. Change in the concentration of oxygen over the change in time. Oxygen final minus oxygen initial. And I'm sorry, I hate to make this just so repetitive, but I want you to get into your head then how we calculate for this rate right here. Okay. All right. So with that said, then I have 0.0011 minus 0. Okay. All over 50 seconds minus 0 seconds. And I get a rate here of 2.2 times 10 to the minus 5 molars per second. Okay, so these are the rates here. Okay, these are the rates. Rate of this is the rate. Whoops, sorry. Let me go get this out of the way. Whoops, not what I want right there. Okay. Okay, so these are the rates then. These numbers then represent the rates at which nitrogen dioxide is decomposing in the first 50 seconds. Okay. The rate at which nitrogen monoxide is forming in the first 50 seconds. And the rate at which oxygen is forming in the first 50 seconds. And we're only looking at the first 50 seconds there. Okay. All right. So with that said, then let's take a look at let's compare a couple of things here. First of all, if you notice then the rate here, when you compare the rate at which nitrogen dioxide and nitrogen breaks down and nitrogen monoxide forms, it's almost the same. And furthermore, then if you take a look at the rate at which oxygen forms, is about half that at which nitrogen monoxide forms, which just so happens to correspond to the ratio of, if you want to think about this, here, 2 to 2 to 1, okay, the ratio that we see with the coefficients. Okay, now I just want to point that out to you because you're going to notice then that that does work, that's going to happen, okay, and we're going to see that, and it does correspond. But when we start talking about the rate laws, the temptation is to use those coefficients for our rate laws, and don't do that, okay, and we cannot afford to do that. So it does work here, okay, and when we calculate for it, we see that it does happen, okay? But don't fall into that trap. In certain instances, we can use the coefficients for the rate law that I'm going to introduce to you, the differential rate law. But again, what I'm giving you here is we have the data, we have collected the concentration, we have timed it. So I just want to point out to you that's what you see right there. Okay. All right. So with that said, let me go ahead then, and this is what I wanted you to key on here is how we calculated for these rates right here. Okay. So let's take a look at how we calculate for these rates right here. What we did then was we took the initial and the final, and I'm going to extend it out here. Basically the change in the concentrations over the change in time, and that's how we calculated for the rates. And we're going to see then that is how we will determine, and let me go ahead and move back here. Okay. Sorry. Okay. And that is how we will determine rates. If you notice that the simplest way that we can do that is that we want to take then the concentration of a particular particular component of the reaction at some time final, and here what I call it T2, and sometimes the initial. Now it doesn't have to be initial and final. We could have done and maybe it'll be good opportunity for us to compare what happens here. What would happen between 50 and 100 seconds? Okay, what would the rate be? And I'm going to show you that in just a moment. Okay, the rate between 50 and 100 seconds. Okay, so it's just two different time intervals, two different concentrations at that particular time interval, and we can summarize it as the change in the concentration over the change in time. The triangle here is the Greek letter delta. It just simply means the change. And here we're comparing the change in the concentration over the change in time. Okay. All right. Let's go ahead then and let's take a look at what happens when you plot this. Okay, so let's take a look at what happens. I'm sorry. So if you notice here, the rate, the consumption here, the rate, the coefficients seem to correspond here. We have a 1 to 1 to 2. Okay, basically then it's a 2 to 2 to 1. Okay, so this is going to be half as much as these here. The rate is going to be about half as fast as the two here, based upon the the coefficient. Okay. All right. So let me go ahead. Let's plot this here. Let's take a look at what we have. Okay. And this is a plot of the reaction that you just saw. Okay, so this we took the numbers and that table there, and we plotted it as well. So here you notice then, and let me go ahead and pull up my annotation key. Okay. What you're gonna notice here then is that here is nitrogen dioxide. Okay, here's nitrogen dioxide right here. Okay. And if we trace this line here, nitrogen dioxide, there it is. It starts out at 0.01 molar. And what do you notice happening? And what we should expect so we're plotting the concentration along the y-axis, time along the x-axis. As time moves forward, that means as you move towards the right across the x-axis, the concentration of nitrogen dioxide begins to drop, which is what we expect. We expect it to get used initially. Okay? Same thing holds true. So that's the green curve here represents the consumption of nitrogen dioxide. If you take a look at the blue curve here, that's the rate. That's the graph plotting the formation of nitrogen monoxide, and the red curve here represents the rate. I'm sorry, the oxygen as it forms. Okay. All right. So as you notice in here, we have both of them starting out at 0, and as time progresses, we start seeing more and more of the product forming. And if you notice then, the slope then for the nitrogen monoxide is a whole lot steeper than the slope for oxygen here. And at any point, if you calculate for the line tangent to each one of these points, you're going to notice then that the slope then is going to be about twice as much, which seems to confirm what we saw with our calculation. That is, nitrogen monoxide forms at a rate that is about 2 times greater than that of oxygen. Okay. All right. So with that said, let's go ahead then and let's compare then. Okay. A couple of regions here. Okay. And let me go ahead and oops, sorry. Okay. And so if you take a look at this region right here, okay, and we trace then the change in the rate, and you can do this. I'm not going to do this for you. Okay. You can find then this right here. You can find then the slope for this line here. And if you notice this line tangent to this point right here. Okay, so if you take a look at this, if you take a look at that point right there, which then we have the concentration of roughly about what that's about 0.006. But what happens at 100 seconds? That's what we refer to then as the instantaneous rate, and we'll talk about this in just a moment. That's the rate at which the nitrogen dioxide is breaking down at that moment in time. Okay. Now, so this is what we refer to then as the instantaneous rate, and we can calculate for that instantaneous rate, and we can calculate for that in a couple ways. We can go ahead and we can integrate. Okay, and for those of you who have taken calculus, we can go and integrate, working from and then setting the limits then at which we would integrate at this point here. But you don't have to integrate. The way that we can find this instantaneous rate right here then is just find then the slope of the line that intersects at that point. So that's what we call then the line tangent to that point, and then we can go ahead then and calculate for that slope and get the instantaneous velocity at that point. Okay. All right. We can do the same thing then, and let me go ahead and highlight that. Here we can do that same thing for whoops, sorry, for this for the rate right here as well. Okay, and then as we do so, and as you do so, you're going to see then that the rate, this slope of this line right here is going to be about, again, 2 times greater than the slope here. And if you notice, this is the negative slope, and these will be positive slope that corresponds then to what we saw with our calculation. Okay. However, typically when we deal with rates, we don't want to deal with negative rates. In order to compare, we just go ahead then and we take the absolute value of the change in the concentration, so that we deal then with positive quantities rather than negative quantities. Okay. All right. So with that said, then let me go ahead and put that out. So the instantaneous velocity is useful for us, and we want to compare then rates at certain moments in time. But typically, what we would do then, and when I introduced to you then the rate laws, we don't really need to deal with instantaneous rates. We can work with average rates. Okay, so typically then with average rates, we just take two concentrations at some point, and then just go ahead and calculate the slope of that line. Okay. All right. So let's go ahead then, and let me introduce you to the first rate law that we will have to deal with. Okay. All right. So we know how to calculate for a particular rate. We can calculate for the instantaneous rate now, and we can calculate for the average rate. Okay. And so what we do with that information is we want to be able, we don't want to be able just to focus in on a couple of points on a graph here, but what we want to be able to do is to establish a law that we can use, okay? That we can use then to compare how quickly a reaction takes place compared to another reaction. Okay? And this rate law allows us to do so. Okay? And what we do then is the rate law is a general rate law here, okay? But it applies. So this is the format that we would use for any chemical process. But if you notice here, we apply this particular rate law to this reaction here. And if you notice then, the rate law then defines for us the rate at which a chemical reaction occurs. Okay? Here is the concentration right here of the reactant, if you notice here. Okay? K then is what we call the rate constant, and N is the order of the reactant, or the order of which, so here it'd be the order of which the reactant breaks down, whereas with the if it were the product, it would be the order of the which the product is forming. Okay, so that's what those terms mean in our rate law right here. Okay, and so if this were a different reaction, we would replace what's inside the here, and we would have a different substance in there. Okay, all right. So what we need to make sure we focus in on as we work through and establish the rate law for a given reaction, that we want to make sure that we focus in on only, for example, here, the decomposition of nitrogen dioxide. Okay, we want to make sure we keep that in mind. And this rate law, because we're looking at the nitrogen dioxide here, we're looking at the decomposition of nitrogen dioxide. What we do not want to happen, okay, is we don't want the reverse reaction to start happening. Okay, we've studied equilibrium. We've talked about it already, and we know then, and this is what I introduced you at the very beginning of this chapter yesterday, is that equilibrium is the process by which everything in the universe strives towards. Everything wants to strive towards equilibrium, which means then as nitrogen dioxide starts breaking down and we start forming more nitrogen monoxide, more oxygen, at some point, equilibrium, the reverse reaction is going to start taking place. Okay? And when that starts to happen, we start the concentration of the nitrogen dioxide then starts to increase again. Okay? So since the rate law depends on the concentration of nitrogen dioxide, we do not want the nitrogen dioxide to start building back up again, because then that will interfere with our ability to study the decomposition of nitrogen dioxide and not the formation of nitrogen dioxide. Okay, so what you want to make sure you keep this in mind then is that when we try to establish this rate law here for any chemical process, okay, we want to make sure then that we want to look at the initial conditions, or as close to the initial conditions as possible. Or the better way to look at it is that we want to look at what happens right before before equilibrium is reached. We do not want equilibrium to be reached when we try to establish the rate law. Okay, so typically what you're going to see then is that the values that we're going to use here for the concentration will typically be initial concentrations or concentrations at the very beginning of the reaction. So from 0 seconds and onward. Okay, and that's going to be before we reach equilibrium. Okay, so this is this form of the rate law here is what we refer to then, okay, as the differential rate law, and I'll talk about this in just a moment. Okay, so this rate law here, again, like I said, we don't want the reverse reaction to occur, and the values that we will use for the constant, okay, the value that we will use for the rate constant, which is K, and for the order, which is N, those are experimentally derived. Okay? They are not taken from the balanced equation. Now, yes, is there a relationship between the balanced equation, the coefficients, and the rates themselves? Yes, we just saw that. Okay. However, the n in our term, that the exponent n, does not necessarily relate to the coefficients, and neither does K. K and N could be, N could be related to the coefficients, but in what we call unimolecular reactions. And we'll talk about unimolecular reactions towards the end of this chapter. Okay? But most reactions are not unimolecular reactions. Okay? And so therefore, we cannot assume that N, our exponent here, is taken from the balanced equation. It isn't. The rate constant and the order number, the exponent there, N, both of those have to be obtained experimentally. Okay? And we will obtain them experimentally, and we will calculate for those as well. Okay? So N can be any integer, okay, and it can even be a fraction. Typically, what we'll do in our class here won't be, and you won't see a fractional integer there. I'm sorry, you won't see a fractional. You won't see a fractional order number there. Not on the AP exam, not in this class. Okay, and K then tends to be then typically it's going to be a positive number and also not a fractional number. Okay, all right. So that's what we have there for the differential rate law. Okay, all right. So with that said, then when we establish the rates here, let's say then that we have here. Okay, so what we have here, then I already showed you then. This is going to be then the rate of consumption for nitrogen dioxide over time. So we can write that then as K over N. Typically, what we would do then is we will look at the reactants only. We will only consider the concentration of the reactants. However, if you wanted to establish the rate for let's say here, for our example here, the rate at which oxygen gets consumed, okay, we can still define that in terms of the rate at which nitrogen dioxide is going to be used up. Okay, so the first rate law then is going to be then the rate law defining the consumption of NO2. The second rate law here then is going to be the rate law that defines then the production of O2. Okay, and there is a relationship between those two, and I want to show you this really quickly. Let me go ahead and open up my whiteboard then to show you that those two are actually related. Okay, so let's go ahead then and let me show you this. Let me clear this up really quickly. I think I saved that. Hopefully I did. Okay. All right, so let's go ahead and let's consider what we have here. Okay. So we have then the rate. I'm going to do this. Okay, of NO2 consumption is going to be then the rate constant there times the concentration of NO2. Okay, raised to the n power. Okay, the rate at which O2 is consumed, we call that one K prime. Okay, and that's going to be the concentration of O2. I'm sorry, rate at which NO2 is still used up. Okay, raised to the nth power as well. Okay. All right. So if you take a look at this here, and what I'd like to do is let me. Well, do we have time to plug in some numbers here? No, we don't. Let me go ahead and I don't think we'll have time to. Let me just go ahead and work this out for you. Okay. So let's go ahead then, and I'm going to let's the rates here. Let's substitute these in. Okay. At some point, the rate of NO2 is 2 times greater, and we saw this, than the rate at which O2 gets consumed. Okay, rate of NO2 then, let's go ahead and substitute that in. That's going to be K NO2 raised to the nth power. It's going to be equal to 2 times rate of O2 is going to be K prime times the concentration of NO2 raised to the nth power. Okay, nth power, not second power, sorry. Okay, and if you notice then, that cancels out right there. Okay, and so we see then, essentially, there's this relationship between the two here. Okay, and we see then that if we wanted to find then the equilibrium, the rate constant for K prime, it's going to be 1/2 of the rate constant for K. Okay. And so there is that relationship there, but typically what we will do, and I'll try to wrap up here, I'm running out of time, but what we typically do then when we talk about rate constants, we just focus in on the rate and the integer and the exponent there, we typically focus on only the rate at which the reactant gets consumed. Okay? All right. So let me go ahead and save this really quickly. And let me go ahead then, and with the little time that I have left, I want to go ahead and share with you the two different rate laws here. Okay. All right. So I showed you how these two are related. Okay. And so what we just defined in there is what we call then the differential rate law. Okay. The differential rate law then is a rate law that takes into consideration then, if you'll notice here, only the concentration. We really don't focus in on the time so much. Whereas with the integrated rate law, which we will learn towards the second half of this class here, we're going to see then that those particular integrated rate laws then we will use. Sorry. If we are going to, the focus of our attention is going to be on the concentrations of the species as it depends on time. Okay, so here then we're looking at only concentration with the differential rate law, with the integrated rate law, which actually, if we integrate this, if we do, for those of you who've taken calculus, what we do is we integrate this differential rate law here, we will get the integrated rate law, and that's why we call it the integrated rate law. And for those of you who are interested, come on by and I'll show you how we do that integration. Pretty quick forward, pretty quick, pretty simple for those of you who've had calculus already. Okay, but so which rate law will we choose? It's going to depend on which one is going to be a little easier for us to obtain. If we have access to concentrations, okay, or time, we can go ahead then and use the integrated rate laws. If we don't have access to time, then we're going to use the differential rate law. Okay. All right. So with that said, then what I'll do then is on Monday, okay, what we'll do then is I'm going to just summarize what we've talked about so far in terms of the differential rate law, and then we're going to get into calculating and obtaining the differential rate law using the experimental values that we have. Okay. All right. So if you have any questions on this lesson here, please make sure on Monday, stick around after. Come by after my 7th period class, and I'll go over this with you. But try your best with it, and we'll get into the math of we'll get into the calculations involving these rate laws next week, starting on Monday. Okay. All right. Very good, folks. Have a good rest of your weekend, and I will see you folks on Monday. Okay. All right. I'll see you. Bye.